Hey, it's Tim the Tutor here from Free Test Prep Online, and in this video I'm going over what I consider to be the most important topic in organic chemistry, and that is how to define and recognize nucleophiles, electrophiles, acids, and bases. Most organic chemistry classes are incredibly difficult because there's no foundational knowledge drilled into your brains on how reactions actually work. Most professors may provide you with a couple of basic ideas, but then once they start teaching reactions, they might throw up a PowerPoint slide and expect you to memorize a bunch of random facts about a bunch of random things that seemingly have no relationship to each other. And that makes organic chemistry seem a lot more difficult than it actually is. So the purpose of this video is actually to show you there is a systematic way of solving problems, but you need certain foundational elements in your brain in order to be able to put these things together in a way that actually makes sense. So that's why I made this video. So we're going to start off with a simple question. What is a nucleophile? And to answer that question, I'm not going to give you some textbook definition that's very technical. I'm going to give you a very practical definition so you can always recognize a nucleophile. A nucleophile is simply a region of a molecule that has excess electron density. But I'm going to even simplify this more. How do you most commonly recognize a nucleophile? So it's great to say, oh, it has excess electron density, but that doesn't actually help you when you're staring at a reaction you've never seen before. So how do you most commonly recognize a nucleophile? Well, luckily, nucleophiles like to advertise themselves. They will literally go out of their way to say, hey, look at me, I am a nucleophile. What you're looking for is a lone pair, a negative charge, or a pi bond. And that's it. If you see a lone pair, a negative charge, or a pi bond, you can say, hey, that region on that molecule at least is a little bit nucleophilic. Now, how nucleophilic it is a different story, but at least if you see a lone pair, a negative charge, or a pi bond, you can say it's at least a little bit nucleophilic. With that out of the way, let's talk about bases. What's a base? And again, I'm not going to give you the very technical definitions. Now, we already know the Bronsted, Lowry, and the Lewis definitions of a base. You can say that it's an electron donor or a proton acceptor. But again, I'm going to go simpler than that. A base is a region of a molecule that has excess electron density. And now we have to ask, how do you most commonly recognize a base? Well, luckily for us, bases also like to advertise themselves. You're looking for a lone pair, a negative charge, or a pi bond. And there you have it. Now you know how to recognize a nucleophile and a base. Okay, I understand. You think I messed up. A nucleophile and a base, not only do I have the same definition for both of them, but I have the same way to recognize both of them, but they're not quite the same thing, are they? Well, no, they aren't, but they're very similar, and they're recognized the same way. So now we can go into the difference between nucleophiles and bases. The first major difference we're going to discuss regarding nucleophiles and bases is how they behave in reactions. As I repeat often, organic chemistry is the science of drawing arrows from negative charges to positive charges. Now it should be abundantly clear to you that nucleophiles and bases are the regions of negative charge that I'm referring to when I say that. So they're always going to be doing the attacking. Now, nucleophiles are going to attack electrophiles. In organic chemistry 1, that's usually carbon, but once you start getting into more and more reactions, you realize it can be any number of electrophiles, not just carbon. And they do so in primarily substitution reactions and addition reactions. Bases, on the other hand, always attack hydrogens, and when they do so, it's in elimination, addition, and in acid-base reactions. In this example here, I have hydroxide, the OH negative anion, and here you can see it is attacking a partially positive carbon. Here, hydroxide is acting like a nucleophile, and you can see in the product that we're getting a substitution. The OH is being substituted in, the Br is being substituted out. In the second reaction, however, we have hydroxide again, because hydroxide, it has 3 lone pairs that are negative charge, so it can be a nucleophile or a base. Here, it's acting like a base. you can see that it is attacking the beta hydrogen on this molecule, and the end result is an elimination reaction in E2, where we create a double bond and we kick off that leaving group. The next difference between nucleophiles and bases is their size. Big, bulky bases can never act as nucleophiles, and the reason why is they are too sterically hindered to attack electrophiles. So let me give you an example of this. On the left, I have a hydroxide. Hydroxide is small. The negative charge is on the oxygen, and there's not a large group next to it. There's just a very tiny hydrogen. So hydroxide can act as both a base and a nucleophile. Tert butoxide on the right, also known as OCCH33, this is a non-nucleophilic base. You see that next to that negative charge on the oxygen, there is a large tert butyl group. That negative charge is prevented from acting like a nucleophile. In other words, it's prevented from attacking an electrophile because that large tert butyl group will get in the way of that negative charge reaching its designated target. So what can it do? It can only reach those hydrogens on the outskirts of molecules, so it can only attack hydrogens, and therefore it will only act as a base. We know that nucleophiles and bases are essentially defined by their region of excess electron density. So in various solvents, we need to discuss how that negative charge is affected. So in polar protic solvents, such as water and alcohols, going down the periodic table actually increases nucleophilicity, but it decreases basicity. You may notice that in both these graphics, the periodic trend for basicity and nucleophilicity is identical regardless of whether we're using a polar aprotic or a polar protic solvent. However, if we focus on the graphic on the left, you'll notice that in polar aprotic solvents, we have decreasing basicity and nucleophilicity, whereas on the graphic on the right, in a polar protic solvent, we have decreasing basicity, but we have increasing nucleophilicity. A polar aprotic solvent is essentially a solvent that does not have any acidic hydrogens. Since polar aprotic solvents have no hydrogens available, they don't solvate the negatively charged anions very well. So the predominant factor from top to bottom on the periodic table regarding nucleophilicity and basicity is the size of the anion. And as the size of the anion increases, it spreads out that negative charge or delocalizes that negative charge in that valence shell, making it less effective as both a nucleophile and a base. In other words, it makes it weaker. However, with a polar protic solvent, we do have hydrogens available, and those hydrogens are going to solvate small anions very effectively. Nucleophilicity, therefore, increases in polar protic solvents going down the periodic table because the negative charge on larger anions is not effectively hidden by the hydrogens in the polar protic solvents. The very last difference between nucleophiles and bases that I'm going to discuss in this video is somewhat exclusive to this video. That means that no matter what textbook you refer to or what class you're taking, you probably won't see this simplified in the way that I'm simplifying it here. And that is that delocalization of electron density due to size, induction, or resonance decreases the tendency of a molecule to act as a base more than it does as a nucleophile. I know that's a lot to unpack right there, and without an example it may be kind of difficult to really interpret what it means. So let's give some examples. On the left, I have three anions that are considered to be more basic than nucleophilic. That is, when they react with secondary alkyl halides, elimination tends to be favored. You'll see that in OR-, OH-, and in that acetylide anion on the bottom, that negative charge is very strong and very localized to a single spot on those molecules. In other words, we did not delocalize the electron density. That tends to favor basicity. On the right, we have four anions that are more nucleophilic than basic. That is, in reaction with secondary alkyl halides, these anions favor substitution reactions. And you'll notice there's a difference between the anions on the right-hand side that are more nucleophilic than the ones on the left-hand side that are more basic. And that is, we have more delocalization of the electron density for one reason or another. If we compare SH- with OH-, sulfur is further down on the periodic table. That means sulfur is larger than the oxygen, so the negative charge is spread out among an orbital that is a lot further away from the nucleus. So it's delocalized due to size, and that makes it more nucleophilic than basic because we decrease the basicity more with the increasing size. With the one in the top right, we delocalize that negative charge due to resonance. So that molecule tends to act much more as a nucleophile than as a base, because again, that negative charge is delocalized. That's the same with the N3-. The N3- has 3 total resonance structures, again, spreading out that negative charge in a much larger region, decreasing its basicity and not affecting its nucleophilicity as much. And then last, with our Cn- or our cyanide anion, the nitrogen has an inductive effect on that negative charge. Nitrogen being more electronegative than carbon, it pulls that electron density away from the carbon. That is going to delocalize the electron density, and therefore it's going to decrease the basicity much more than it decreases the nucleophilicity, which is why cyanide tends to always act as a nucleophile and not a base. Now that we've had a thorough discussion of the difference between nucleophiles and bases, let's move on to electrophiles and acids. Luckily for us, recognizing an electrophiles and acids and telling the difference between them is a lot simpler, because electrophiles and acids are recognized differently. So what is an electrophile? Well, if a nucleophile is a region of excess electron density, an electrophile must be a region of a molecule that lacks electron density. Now I'm going to clarify that when we refer to electrophiles, we cannot refer to hydrogens. Now, how do we most commonly recognize an electrophile? Unlike with nucleophiles, which like to advertise themselves with a lone pair negative charge or pi bond, electrophiles are a lot more subtle. The exception, of course, is with the positive charge. If we have a carbocation, for example, we will see that positive charge on the electrophile. Other than that, however, we need to be a little more discriminatory in what we're looking at. So a partial positive charge is another way to recognize an electrophile. However, here we're looking for really a difference in electronegativity between 2 adjacent atoms on a molecule. For example, if we have a carbon bonded to a nitrogen, an oxygen, or a halogen, we can say that the carbon is going to be partially positive because the nitrogen, oxygen, or halogen that's bonded to it is more electronegative. So in other words, those carbons in those situations are going to be partially positive and electrophilic. But it doesn't advertise itself that way. We need to make sure that we figure that out by looking at those 2 adjacent atoms. Last, we are looking for an incomplete octet. An incomplete octet is an atom that doesn't have a full set of 8 valence electrons when you consider all its bonds and lone pairs. For example, the aluminum on aluminum trichloride, which is AlCl3, the aluminum only has 3 bonds. It doesn't have any lone pairs, however, so it only ends up having 6 valence electrons. That means it has an incomplete octet, which makes it an electrophile. Now let's move on to acids. So what is an acid? Well, an acid is simply a hydrogen lacking electron density. That's why we can't include hydrogens in our definition of an electrophile, because that would infringe upon what the definition of an acid is. So how do we effectively recognize an acid or determine its strength? So acids are a lot more complicated when we do rank them. In fact, I have an entire other video dedicated to ranking acid strength that you should probably watch, but here is the essentials you need to know. The easier it is to remove a hydrogen from a molecule, the stronger it is as an acid. An acid is difficult to rank directly without a pKa table, so it is done qualitatively by evaluating the strength of its conjugate base. And we have this phrase, the stronger the acid, the weaker or more stable its conjugate base. Once again, for a full discussion on ranking acids, see the video, Ranking Relative Strengths of Acids and Bases. Now that you've learned about nucleophiles, bases, electrophiles, and acids, let's do a short quiz to see how much you've actually learned. So I've drawn ethanol on the page. Is ethanol an acid, a base, a nucleophile, or an electrophile? Go ahead and pause the video and think about it for a minute, and then come back, unpause it, and see what the answer is. If you decided that this was a trick question, then you were correct. Why? Well, there are two lone pairs on the oxygen, so it can act as either a nucleophile or a base. And there are plenty of reactions showing it acting as a nucleophile or that show it acting as a base. So it could be both a nucleophile and a base. However, there's also a hydrogen bonded to an oxygen, so that actually makes it partially positive on that hydrogen and therefore kind of acidic. So ethanol can definitely act as an acid in certain situations as well. However, there's also a carbon bonded to that oxygen, so the oxygen's more electronegative than carbon, which makes that carbon partially positive, and a partially positive site on a molecule is electrophilic. So in other words, ethanol is nucleophilic, basic, electrophilic, and acidic. And this brings me to my key point, and that is that molecules, we can't evaluate them as a whole. Molecules can behave in many different ways. So we can't look at them as a whole, rather we have to look at their individual regions and analyze those different regions separately. Different parts of molecules can react with different reactants in different ways, so we need to be aware that the molecule itself is none of those things. Different parts of the molecule can act in certain ways. Back on the first slide, I mentioned that this video is probably the most important video for you to understand. So why is all of this so important? Well, being able to recognize negative and positive regions on molecules might be the most important skill that you can develop in organic chemistry, and it isn't hard to learn. Almost every single reaction that you encounter in organic chemistry 1 or 2 is going to require you to be able to draw an arrow from a region of excess electron density, the nucleophile or the base, to an area deficient in electrons, the electrophile or the acid. And more often than not, a reaction mechanism is just a series of steps where an arrow is drawn from a negative region to a positive region over and over again. Trying to memorize hundreds of reactions is a terrible idea that will inevitably lead to incredible stress or failure or both. Being able to work your way through a problem by recognizing the reactive sites on the molecules is much more effective and efficient, and will give you a place to start when your memory fails you on tests. This is why this is so important to develop this skill early and just to consistently apply it over and over again. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.